Hi, my name is Andy, and I will be presenting approximate and exact methods in hypersonic and viscid flows. Um, Essentially, this presentation is an outline of chapters 4 and 5 in the textbook named High Temperature Gas Dynamics and authored by John D. Anderson. Um, these two chapters are inherently pretty math heavy, so just be prepared for that, fair warning. I made the effort to try and be as concise as possible, but still not really cut corners on like the logic behind these methods. So I focused my time on just what are the equations, what are the logic, what logic is used to simplify this if needed, and what procedures are taken out to actually solve this. Right, I skipped any extensive derivations or really examples as well. This is just trying to get uh, us exposed to just what the methods are and how they work. This slide's pretty straightforward, just an outline of the presentation. One comment I will make is that in chapter 4, when they say approximate methods, what they mean is that they are simplifying the Navier-Stokes equation somehow. Right, they're doing it either through the geometry or something about the physics to not completely model the Navier-Stokes equation. In chapter 5, there are no simplifications of this Navier-Stokes equation. We are trying to model the real thing. Um, that being said, we know that there is no analytical solution for the Navier-Stokes, the true Navier-Stokes equation. So chapter 5 is actually a numerical methods chapter. It's just called exact methods because, again, we're not simplifying the actual equations. We are trying to model the real thing. Um, we're not neglecting any physics. We're not simplifying the equations by neglecting physics or geometry or something where we're trying to really model that. It's just through a numerical process. In the previous chapter, we went over the oblique shock waves and surface inclination methods. Um, these methods are based mostly on algebra, and because of this, they're limited to just communicating local flow information. In order to try and model an entire hypersonic flow field over a body, we need to solve a system of PDEs, of partial differential equations, or integral equations. Um, so that's what this method's about, right? These analytical methods provide exact or approximate solutions. As discussed before, that the difference between that is just, are we simplifying the physics somehow, or are we trying to solve the actual Navier-Stokes equation? Um, and specifically for this section, the major advantage over using a numerical method just like a CFD calculation is it gives you much more insight into what parameters actually change the flow field solution. So now we're into the meat of the presentation. We're going to start talking about these methods. The first thing I want to talk about is this concept called the Mach number independence. And essentially what it's saying is that at high free stream Mach numbers, aerodynamic coefficients and other related quantities will become independent of Mach number. And then we're going to quickly go through that derivation process. So um, I first want to start by just reminding you guys of what the conservation equations look like, right? These are your Navier-Stokes, plus you have your conservation of mass and your energy. You have your oblique shock waves. These equations are starting points for deriving this. So the first thing you want to do is just non-dimensionalize your variables. We start with our x, y, and z, just over the length, and then our free stream conditions. And then we just take that, multiply the original conservation equation by a clever form of 1, and we get to here. This process is repeated for the other ones. And the result is right here. For a steady inviscid flow, we know that the dot product between the velocity vector and the normal vector to a surface must equal 0. In layman's term, it means that it's necessary for the velocity of the wall to be equal to 0. In math, we describe it using this equation, right? Again, it's just the dot product expanded, and then we can normalize that by just dividing by L. Or no, I'm sorry, we divide by the free stream velocity here. And And again, we have a normalized version of this boundary condition. So if you're starting to recognize a trend here, you're right. Our next step is going to then be to normalize the shockwave conditions, the oblique shockwave conditions. What's important about these is that these serve as inflow boundary conditions to the right hand, to the post shock portion of the flow, and that's going to be a very important concept moving forward. So we're at the oblique shockwaves. The first thing we're going to do is just redefine the left-hand side of the oblique shockwave equations, the actual pressure comparison to pre-shock and post-shock in terms of our normalized variables. And then we're just going to solve them and plug them into the oblique shockwave equations. And then this is our new form. Now the normalized oblique shockwave equations are repeated right here for convenience. Now, if we take the limit of the free stream Mach number as that Mach number approaches infinity, we result in these equations. So what that's telling us is that there's going to be some asymptotic value for Mach number. So it's constant, so they become independent. Explicitly stated, if you notice, these formulas don't have Mach number in it at all. So that means they're independent of it. And it is and then we can further define the aerodynamic coefficients that are based off these values to be independent of Mach number as well. Our next approximate method is called hypersonic small disturbance equations. Essentially what we're doing is we're going to rewrite the Navier-Stokes equation in reference to these perturbation velocities, which is essentially a change in velocity when comparing to the free stream. And here are some considerations. The first one is you need to make sure you're going over a slender body, something that has a sufficiently high length to diameter ratio, which in turn is going to give you a high lift to drag ratio. The second thing that we need to do is define our perturbation velocities. So for our x component, it's just going to be the free stream plus this change in velocity. Now, for our y component, it's going to be 0 plus this change in velocity. It is 0 because in this method, the free stream velocity is assumed to be aligned with the x-axis, like so. So yeah. And then the next thing we need to do is to define a flow tangency condition. So assuming that f of x is that y is given by f of x, this curve of the body, we know that at that curve it needs to equal the perturbation velocities, right? Your dy needs to equal your change in y, and your dx needs to equal your change in u. So because we're using a slender body, we can assume that the free stream velocity is much bigger than our disturbance in the x direction. So we can basically make u prime a 0 value, and then the dy dx condition is approximated by just v prime over v infinity. So again, in this method, we're going to normalize our variables again. In this section of the book, they do give us a little bit of insight of how they do that. Essentially, what they're doing is they're trying to decide what equation they're going to use to normalize each variable. And they do that using this method, this thing called order analysis, where that's what this big O is. If you see like a big O and then a function of something, like for example, the top one, you could read that as dy over dx is of order d over L. And essentially what you're trying to say is that dy dx is going to follow the behavior of d over L. So you can kind of roughly match those two curves. So that's kind of the basis here. So right, they say dy over dx is of order d over L. So they know that, so it's convenient to just define d over L as some parameter tau. Subsequently, we can say that dy over dx is of order tau. Now, what we're going to do is kind of do the same thing for these equations for the other input parameters. So the same thing, first thing is the y velocity. Again, if you solve for y, you can see that, again, from our previous flow tangency condition, you can see that v prime over v infinity is of order tau. So it's going to, that disturbance that you see is going to be of order whatever your slenderness ratio is. So yeah, so they take that into account and they basically solve for a relationship including Mach number. And they do the same thing. They could say that v prime over a infinity is going to be on the order of the free stream Mach number times this tau. So it's going to follow the behavior of these quantities. In this slide, we're doing a similar sort of order analysis for the other boundary conditions that are relevant to the flow field, and I won't walk through all the algebra here, but I do want to comment on at least the first equation, where if you see they have sine of beta is equal to sine of theta. So the shock wave angle and the deflection angle are approximately equal. Then using the small angle approximation for a sine, we'll say that they're equal to theta, which just happens to be equal to dy dx, which is our tau parameter. And that's just that's key to being able to come up with these other normalization equations. So yeah, right, we have one for normalized pressure, normalized density, normalized u velocity, and normalized v velocity. With that in mind, we start the normalization process by rewriting the governing equations in terms of the perturbation velocities. We then substitute the newly normalized variables that we just derived into these same equations. On this slide, we use a little bit of logic to simplify our newly derived conservation equations. Essentially, we know that for a slender body, tau is going to be less than 1. So if you square that, it's going to be an even smaller number. So it's safe to assume that it will be much smaller than 1. We use that to justify ignoring it. And thus we arrive at this set of equations, which are the hypersonic small disturbance equations. Just some comments. Based on just what I said, right, these are limited to a slender body. You cannot use this for a blunt body problem. And because of this non-dimensionalization, it has to be in the hypersonic regime. It's going to depend on that, on these limiting quantities that we derived earlier. In this section, we're going to talk about the hypersonic equivalence principle. And it's essentially a way to compare flows, a flow similarity concept. Fluid mechanics loves to do this. They love to compare flows, right? That's where things like the Reynolds number, the Nusselt number, the Newton number, the Weber number, right? All these are based off that idea. So this is a similar framework for comparing flows in the hypersonic regime, in the inviscid hypersonic regime. I'm going to skip this derivation because it was pretty lengthy, but I do want to mention that in this, they do formally define the hypersonic similarity parameter as m, as a free stream Mach number times tau. And then they take all the equations that we just derived, the non-dimensional governing equations, the non-dimensional oblique shockwave equations, the perturbation governing equations, and the boundary condition at the wall. They take all those equations and they derive these aerodynamic coefficients explicitly. And at the end of this derivation, they talk about this basically, I guess, theorem or this framework for comparison, the results of the framework. And essentially for a 2D flow, you're going to look for matching values of, rewind. The results of this derivation are as follows. For 2D flow, you could say that the coefficient of pressure over tau squared is going to be some function of gamma, this k value, and then alpha over tau. And you could do the same thing for lift, same thing for drag. Notice drag is to the third, it's tau to the third. That's the same function. And then for 3D flow, they do the same thing. You have coefficient of lift over tau, and this time it's a function of gamma, Mach number, and tau, not the similarity parameter, but separately. And then again, this alpha over tau. So then they derive these expressions. You could say for any two flows, there's going to be some form of this. Then if those, for 2D flow, if they're matching, if you have matching values when referencing the plane form area, you have hypersonic similarity. There's similar flows. And then for 3D flow, same thing, but you have to reference the base area. So now we're going to discuss blast waves theory. This kind of starts by looking at another angle of the hypersonic equivalence principle. So if you look, so on the left-hand side, we have a set of equations. This is unsteady flow in the YZ plane, which is the perpendicular plane to our free stream. Right, so if you look at that 2D plane flow in an unsteady form, and we compare it to the steady form 3D flow of the perturbation conservation equations, other than a few differences in how we define our normalization variables, the equations are essentially identical. And this is the mathematical justification for the hypersonic equivalency principle. So this slide is going to illustrate the concept I just discussed. If you look at the very first row, this is essentially the flow at the leading edge of our cone. So right in the 3D flow, it's at the leading edge of our cone, but in the 2D flow, it's a blast wave at time equals 0. Again, this is the perpendicular plane to the free stream. So then in the middle slide, we're a little further downstream of the nose along the body, and now in the 2D plane, unsteady, this is at some time where we have a blast wave, where we have a wave. And then in the third row is just a further time step where now our wave has further expanded and we have a bigger radius. So yeah, that's kind of an illustration of how we're connecting this unsteady 2D flow to a steady 3D flow. In this slide, we are extending that same hypersonic equivalence principle to a blunt body problem. Again, we are taking that 3D steady flow and then mapping that onto the perpendicular 2D unsteady flow. And these two flows are equivalent. When comparing this flow field, the blunt body flow field to the slender body flow field, the main difference is really that that initial slope, of the shock wave, and a blunt body is a better approximation because that slope is so extreme at first that you can use that to measure an instantaneous, energy release. So that's just a, that instantaneous nature of it is like more of an impulse sort of reaction, and that's just a closer approximation of what a blast wave is like. So that's all that's really being pointed out with these figures. So now we move our discussion to a topic called thin shock layer theory. The first thing we want to do is really define what a shock layer is. So it's that region of flow field behind the shock wave and in between the wall of the surface at the of the flow of the body. So revisiting from the oblique shock wave theory, what we need to know is that as your free stream Mach number increases, this region is going to have a smaller deflection angle and will also be more compressed air. Right, so you're going to be compressing more air. So what this means for hypersonic flow is that we expect this region to be very small. In fact, it is shown that as the Mach number, the free stream Mach number approaches infinity, our gamma approaches 1, and the beta, the shock wave angle, approaches 0, the shock layer will become infinitely thin and infinitely dense. In this case, we can assume that the shock wave, the shock layer, and the surface of the center body all approximately have the same shape. And then this is the assumption forming the basis of thin shock layer theory. So now we're just gonna set up some nomenclature with respect to thin shock layer theory. First, we just need to consider a curvilinear coordinate system such that the x-axis is parallel to the shock, so you're moving along the shock, and the y-axis is perpendicular to the shock. Then for such a coordinate system, the conservation of momentum equation is as such, where r equals a local streamline radius of curvature. Given that we're evaluating this with a thin shock layer assumption, this streamline radius of curvature is the radius of the shock. It's also the radius of the body. But this is an important simplification. On this slide, we're going to go over a procedure known as Maslin's method. This just seems to be the standard procedure for actually calculating, a flow field under the thin shock layer theory. So the first step is to assume a shock wave, as in the figure shown. In this respect, Maslin's method is an inverse method, where a shock wave is assumed and then we calculate the flow field body that would fit that. So the first thing you want to do is you start at a point A along the free stream, along the streamline, before the shock wave, or behind the shock wave. So essentially, we know all the flow field properties here because they're at the free stream conditions. Then step 2 is we pick a second point along that streamline, with sub B, such that it's in between the original point and the wall, and such that it's inside the shock, the shock layer region of the field. At this point, we calculate the pressure by just using the simple interpolation formula. And since we know they're along the same streamline, we can calculate the enthalpy at point B, because there should be a state of constant enthalpy, or it should be along a curve of constant enthalpy. We use it to calculate enthalpy at point B. So yeah. Then in step 6, we just calculate all the standard thermodynamic information at that new point, now that we have the necessary data. And step 7, we are going to calculate the enthalpy. We're then going to use the enthalpy to then calculate the velocity at that point as well. Now, at this point, we know all the flow quantities at point B. We need to repeat this process for all the other points in between the wall and the flow field. Then from here, we could just find the y coordinate of any desired point by integrating the definition of the stream function. Then this procedure is repeated for however many flow field points we need in our calculation. So now we're moving on to chapter 5 in the book, titled Exact Methods. So just some quick notes. Everything we described before, we have just gone over, it can be considered a quote-unquote classical fluid mechanics methods, right? These are methods that existed before any sort of significant computational power existed, and as we discussed with detail, these methods are useful, but they require significant simplification of the physics, right? We're missing details by using these calculations. So that's where these exact methods come in. And again, these exact methods does not mean an exact analytical solution. For the Navier-Stokes, such a thing does not exist. They're still numerical methods, but they are an attempt to not simplify the physics of the Navier-Stokes. It's trying to capture everything just using some numerical algorithm. So the first method we're going to discuss is called method of characteristics. This is a standard, I think, numerical method. I've seen it several times. And in this book, they are kind of assuming that you have knowledge, you have an idea of what it is. And essentially, I don't have too much of an idea, but from my research, I have determined that you're essentially solving a PDE by reducing it to an ODE. Right, so you're reducing that dimensionality again. And it's important to note that this method is useful when that system of PDEs is hyperbolic, which ours in fact is. And again, where the compatibility equations that we're going to talk about are going to map the steady 2D or 3D flow to one unsteady dimension before. So it's based off the same hypersonic equivalence principle. And then for this problem, the math is well posed because we're going to have that initial data line of data, right? We're going to know all the flow properties at some inlet condition, and all we have to do is march along like these streamlines that and just kind of iterate down that process. These streamlines are going to be characteristic lines, or they could be shockwave lines, that sort of thing. So MOC is like it's not a set way to do it. There's definitely different. It's very flexible. It contains like a hierarchy of ways to do it. The simplest way is a 2D model with steady and irrotational flow. But for a hypersonic flow, we do need to consider rotationability, right? Vorticity is very important. And we will discuss that a little further. In fact, we will discuss it on the very next slide. So essentially, in a hypersonic flow, you're going to have these strong entropy gradients. They lead to rotational flow, which then justifies the need to have a rotational method of characteristics. And then here is just a little bit of knowledge here is that, right, we know that as the shock strength increases, as the free stream Mach number increases, so that's going to give our shock wave a curvature, and that curvature is going to exaggerate entropy changes along different streamlines. This effect is more exaggerated in blunt bodies because you have a bigger stagnation region, again, going back to a hypersonic external flow. And specifically in a hypersonic blunt body case, this is severe. It can be an extreme problem, or it's just severe. And then this flow field can be calculated using Krokow's method, right? Which you basically have a gradient of your enthalpy, and you have your vorticity, and that sort of thing considered in the equation. So now I'm just going to try and power through the procedure. So step one in method of characteristics is to start with an initial data line that is completely wholly in a supersonic region of the flow. So in case A, if you're doing a flow over a slender body, a slender body with an attached shock at the nose, you can assume all the area in the immediate vicinity of that shock to be supersonic, and then you could just find that shock solution using the Taylor-Machel conical solution. Now, in case B, if you have a blunt body with a detached shock, you have to consider a stagnation region towards the center, towards that leading edge of that body. And you're going to have to carry out a full blunt body solution method to be able to calculate what this initial data line is. For the sake of time, I've left both of these derivations out of the presentation. The book does not mention Taylor-Machel from what I've seen, and the blunt body problem was a pretty long section, so I guess I'll leave it up to the reader. So yeah. So step two is starting from the initial data line, step down the stream along the characteristic lines. The unit process is going to be one iteration of this. This is going to be an iterative process. And then I have the parameters described here. So the procedure described here. The first thing you're going to do is you're going to take points 1 and 2. Both of those points, we know all our flow information there. This is including our streamline angles and our Mach angles that can be easily calculated. So then we're going to use this information to calculate the Mach waves, and we're going to label their intersection. The Mach waves labeled C minus and C plus, right? Because it's going to have a in both directions. And then we're going to label the intersection of those lines 0.3. So the next thing we do is we're going to assume the streamline theta 3 to be the average of theta 1 and theta 2. Then on this streamline angle, with this assumed angle, we're going to trace backwards until we get to the line that intersects the connects point 1 and 2, and we're going to call that point 0.4. For rotational flow, this streamline is also a characteristic line. So we will want to calculate flow properties along this direction. So now we can calculate the flow properties at 0.3 using the compatibility equations across characteristic lines. These equations are derived from the Euler conservation equations, and after some extensive derivation, they come out as follows. Right, you have along the Mach lines, you have this dp term plus or minus d theta plus or minus j sine, blah, blah, blah. And then along the streamlines, you just have a constant change in entropy, right? You cannot have a change in entropy across streamline. There is more to consider here, but again, for the sake of simplicity, I just kind of said, you have to calculate these properties according to the system of equations, essentially. I guess just a comment on what there could be more to consider is so the constant entropy equations, there are alternate forms of that, and then there's a bunch more algebra that I just don't want to dig into at this moment. And then step 5 is to just repeat steps 2 through 4 until a convergence condition is reached. For each iteration, what you're going to do is you're going to update the slope, your Mach wave slopes, based on the average of theta 1, mu 1, theta 3, and mu 3. Right? Theta 3, again, as mentioned before, theta 3 is found from the line traced back to 0.4 in step 4. So once we've reached convergence, we can say that 0.3 is in the right location and it has the correct fluid properties. One question that I still have unanswered from reading through the book, it might have been mentioned, but I didn't catch it myself. I'm not quite sure how convergence is measured, but I think that's an important, I guess, question to follow up here. But yeah. And then the very last method that we're going to talk about is correlation for hypersonic shock waves. A few slides back, I mentioned that I was going to skip over the blunt body problem just because it was too much. But this method provides a pretty good approximation for that, and this is just like an engineering code or like an engineering equation, right? It's based off of correlation, and then we kind of edit it according to some parameters, and I'm gonna kind of describe that procedure as well. In this slide, we go over the procedure. We start going over the procedure of evaluating a hypersonic, flow field using this correlation method. In step 1, what we're going to do is we assume a hyperbolic shock shape according to this equation, and then we also assume all other velocity. We assume that wave velocity is 0 all other grid points. Really, just some nomenclature on this equation. R sub c is the radius of curvature of the shock. Delta is going to be your detachment distance from the body. Beta is the shock angle as before, and then x and y are just Cartesian coordinates of the shock. So then our second step is to just calculate our initial flow conditions at the shock grid points attained using the shock oblique equations. Right, so based off the shock wave structure that we just assumed and its angle, and some of its geometric information, we can calculate we can kind of calculate the P2, the pressure right after that, and then that's how we're going to do that. Step 3 is to assume a Newtonian pressure distribution along the body. And then step 4 is just to interpolate the pressure from the shock wave to the body in that shock layer region. Assuming a linear velocity variation along the surface, we're going to start with the 0 value at the stagnation point and ramp up to an assigned velocity value at the last point downstream on the body surface. This last value can be either the free stream value, or it could be calculated from a wedge flow or a cone flow, what you would expect there. Step 6 is to then interpolate all the velocity values from the shock wave down to the body. Again, interpolating the velocity values in that shock layer region. Step 7 is to calculate temperature at each node. Again, each grid point using the equation for adiabatic heat transfer. And the very last step is to just obtain density at each point using the perfect gas equation, right? Just your P equals rho RT. At that point, you have solved your flow field.